What are you behind on? What do you still need to finish by 11:59 tonight? For most of you, it is quite a lot. For most of you, it is quite a lot. So let's stop wasting time and let's start using time. For those of you that are totally caught up and have absolutely no questions whatsoever, you can be listening and making sure that how you did the problem was accurate and doesn't have any holes in your argumentation or in your work or in your process. But you can also have the 3.4 Jamboard open and ready to go because we have already kind of started those notes. And so you can be setting up those notes for today because that's where we're going. Everybody has something to do for calculus. Here we go. In 3.2, I have questions on 8 and 11. So going down to find number 8. Wherever he is. Here he is. Okay. Number 8 gives me the polynomial function x squared minus x minus 72. And it asks me things about secant lines and tangent lines. It asks me, it asks you about secant lines and tangent lines. Why? Because of MVT. MVT is the big player in section 3.2. MVT, we went and did a problem all together yesterday. You guys went to the boards and you did a problem, actually 3 multiple choice. 1 was a straightforward one, 2 were concepty. My BC kids, as they went around the room, every single group got a 2 out of 3, with most of you missing the exact same problem, which makes sense because you all went around to all the boards, etc. But we did go over those answers already, and once again, they are in your Jamboard. So then, picking up with the MVT homework, MVT tells me what? If a function is continuous, which this one is, because it's a polynomial, and the function is differentiable, which this one is, because it's a polynomial. Technically, polynomials are continuous and differentiable for all real numbers because they don't have any limited domains, so I don't have to even worry about the open, the closed, and all that sort of jazz, even though that's a part of my theorem right up here. Then, what does MVT say I'm allowed to say? F prime of what? What is the conclusion of MVT? What does it guarantee? If that and that are true, then what is true? There is a C in between A to B such that F prime of C is equal to what? F of B minus F of A all over. Okay, someone tell me some description of who, actually we put it in blue because this is very much a calculus thing, the other side is very much a before calculus thing. Someone give me a description for what F prime of C represents. There are lots of different possible answers. Someone tell me something that means. Okay, good. We're going physics. That's not even the easiest one in my mind, but yeah, good. Instantaneous rate. That's physics. But we've also been doing what in calculus for almost an entire semester now? Yeah, derivative. It's a derivative, right? It's a derivative. It's an instantaneous rate. And it's also a slope of who or what? Tangent line. Hey, if you're in number 8 right now, letter C is the tangent line. You have a forever card for that. What's the other side? Who's this guy? Now, instantaneous rate. Average rate.
Beautifully done.
Change in F over change in. One way of thinking about this is change in distance over change in time. Now that would be applying it to different variables, but still, this is an independent, which is like an X, which is also like a T. This could be like a position function, so a change in distance. So it's a change in quantity over a change in dependent variable over a change in independent variable. The easiest one is miles per hour. That most of you think of with rate. It's an average rate. We don't have a calculus word for it because it's not using any calculus, but we can still talk about the slope. What is this the slope of? It's 2 points that we connect. It's going to cut through the graph. What's that line called? Secant line. Good. All right, so let's check and see how you guys did this problem. Because it says make me some lines. What lines? Well, a couple different ones. The first line, well, pause. What do you know about lines? I told you ever since pre-cal, actually, for the kids that are going to have me for Algebra 2 and Pre-Cal and Calculus. I told them in Algebra 2 also. And actually, for the kids that are having me in Algebra right now, I guess there's not many of those, but there are a few that had me in Algebra. Had me again in Algebra 2. Oh, never mind. Alexis was over there. Just kidding. Is there anybody else that I had in Algebra that I'm having in Pre-Cal right now? Oh, maybe not. Would have been possible. I actually showed this and told this in Algebra 1 as well every time I teach it. The most important, useful equation of a line is point slope. And how does point slope go? I started it. Just read what I wrote. Read what I wrote. Y minus y1 equals m times, not plus, minus, think about it. If you were to divide, don't you need for slope a change in a difference of y's and a difference of x's? I have to have subtractions because of the slope formula. And I plug in stuff. So, they give you a couple points. Sarah, do you have it right there? What are the points they give you again?
-7 and -16 and then 9 and 0.
It was -7, not 17?
No. Okay. -7 and -16.
I just remembered it wrong. -7, -16?
Yes.
I mean, all I need for point slope is whatever point you want that's on the line. So, I mean, can we all just say 9, 0? Looks a lot easier. Is that cool?
Yeah.
Okay, so let's throw in 9, 0. So we end up with y minus 0 is just y equals m times x minus 9. That will give me any line that goes through 9, 0, so now just put in the right slopes. The right slopes being, well, for the tangent line, no, they ask you for secant first, right? For the secant line, I go find my m for a secant, which is f of b, careful, 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 b's and a's. A lot of you are getting used to seeing A and B like this, but this is not an ordered pair. This is an interval. Technically, this means for all x's between A to B. This is not an ordered pair, once again. It's a beginning x and an ending x, or a beginning time and an ending time. It's interval notation, so I need to say who is my A and who is my B. The y value is the f of A. The y value is the f of b. So then all I have to do is just plug in all my different things. Or just say, wait a minute, I know how to find this slope. How do you find slope? y2 minus y1 over x2 minus x1. If you don't want to think about the formula, it's the same thing. The second y minus the first y over the second x minus the first x. So y2, that's 0, minus y1, that's -16. All over x2, that's 9, minus x1, that's -7. My slope of my secant line is 16 over 16, which is 1. So for my secant line, all I have to do is throw in a 1 to the end spot. And then write out the whole y equals thing. And then for my tangent line, how does that process change drastically from all that you've done in calculus? In the olden days, we would do y2 minus y1 over x2 minus x1 and cut through the graph and say, it's an average. It's the best we can do. But what do we do now with calculus? We say we don't need to go from one point to another. We can stay at one point and find a slope at that one point. But how do we find a slope at one point? First of all, Sarah, which one are they asking for the tangent? Tangent at or of which?
The equation of the tangent line through C.
Through C. And does it tell you who C is?
No, that's what you find
Okay.
C for part B.
Got it. So then for a tangent, they want us to find it at C. I can't do C minus C, and then f of C minus f of C. That would be 0 over 0, keep going. So instead I take a derivative and plug in the C that we find. So therefore your derivative would be, you guys know this, give me a derivative, pop off real fast. 2x minus 1, but it's 2c minus 1. And all I need to do is find the C. Now question, Sarah, in part B, was it the NVT C? Like, is that what they're having you find?
Yes.
Cool. So then they had you do a quick break from finding all your different lines to go ahead and do NVT, which says take f prime of C, which we just found, 2c minus 1. Set it equal to, wow, board, what's going on? idea what's going on my board? Is it my computer? Oh well. You set f prime of c equal to what for MVT again? Set f prime of c equal to what? The slope of the secant line, which I already found to be 1. So I can go ahead and just say that whole thing is equal to 1 with some quick algebra, which would add the 1 to the other side, and then you would go ahead and get c by itself by dividing by 2. You would get c is equal to 1, and so therefore, for this problem, I would just go ahead for part C and just plug in. Is that a 21 or is that a 2 times 1? So that's why we put parentheses in math, cool kids. It's not 21, it's 2 times 1. It'll be very confusing if you don't show it somehow. And then PEMDAS would tell us, oh, no big dealio, 2 times 1 is 2, minus 1 is 1. That's the slope of my tangent line, and that's what I would put into my M spot. Sarah, how are we doing? Does that get us all the way through? If you guys notice, the slope of the secant line was 1. The slope of the tangent line, wait a minute, how'd they get 73? Question, does the tangent line go through 0, 9? Does the tangent line go through 0, 9? I see you, Andy, I'm coming. No, the tangent line skims and only hits the graph at 1 point. Ah, struggle bus, guys. What's the 1 point that this tangent line's going to hit? It says the tangent through what, Sarah? C. Oh, stink. Well, who is C? I don't know. I need to go figure it out because I need to know the y value at C. I need to know the derivative at C. Oh, hey, I just found that, but we'll still write it out. A tangent line doesn't cut through the graph. It's not going to be cutting through these 2 points that they gave us. Instead, it's going, sorry, not equals, that's times. Y minus y1 equals m times x minus x1. We did find c is 1, so we'd have to come back up here and say, oh, hey, what's f of 1? 1 squared is 1, right, cool kids? Minus 1 is 0. Minus 72. Oh, isn't that going to be negative 72? So if that's negative 72, which a minus and negative is a plus 72, then I would plug in the 1, I would distribute it, that'd be a 1x, minus 1, minus another 72, there's your minus 73. Be careful. When you go to make the match down here, you are going to have secant lines that are cutting through between 9, 0 and your negative 7, negative 16. All of them have the right, wait, where's your secant line? Forget him. Secant, 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 cutting through the graph. Oh, did you need to do any work to get part D right? Doesn't MVT guarantee whatever your secant slope is, a tangent slope would have to be the same, aka parallel? There's only one graph that even has a parallel. Well, forget that. That's the MVT one. It's the parallel one. Some of you might have actually even worked backwards from that and been like, haha, I know the answer and I didn't do any math. If you understand the MVT concept. Andy, go ahead.
You said the tangent equal to 1. Is that because of the slope you used?
I said the tangent became or was, or I solved for it and got it to be 1. Because I was trying to find it at C, which Sarah said was the part B. My part B, we set the derivative equal to the average, and we solved and figured out that that was the point they were talking about. Does that make sense, kind of? But then for my tangent line, I couldn't just plug in that to the derivative. I also had to plug it into the equation of the line as well, because the tangent is going through a different point than the secant. All of this was leading you up to a graphical representation of MVT with a secant and its guaranteed parallel tangent. Here it is at a glance. Any last minute questions before we move on? Sarah?
Oh, I was just going to ask, is the 3.3 going to 3.3 or 11.59?
I think the MVT was supposed to be due at 3:30 because you guys were just catching up, and I think 3.3 is supposed to be due at 11:59, just in case you need extra time on it. Oh, my bad. I just didn't change it. Thanks, kid. Okay. The other question that was on this homework was number 11, yeah? Why is it a yes? If you guys were to look at this one, that's the very first question before we even do MVT. Otherwise, we can say NA and life is good. Some of you tried that. It didn't work, and you're like, oh, I have to solve it. Slackers. Anyway, why does it work? X plus 9, there's nothing that's going to make that DNE. It's not in division, it's not in a log, it's not in a tangent, it's not under a square root. This guy says all real numbers. Why is this not quite so nice? How do logarithms have limited domains? To know if f is continuous, we have to look for any discontinuities. What does Ellen's basic graph look like? Rubber card number 2. He's the swoopy. If you don't know ln, think of E. Look at your calculator. ln's a button, E's right above it because they're inverses. Isn't E the exponential swoop, exponential growth? Worst comes to worst, you can think about the COVID curve if you were at all informed during the past 2 years, year and a half. The COVID curve goes up, exponential growth, and then it starts to taper off because there's a limited population in the world. They were trying to flatten the curve and have this happen more gradually so that it wasn't quite so extreme to overwhelm healthcare. That was the whole original flattening of the curve. They didn't want it to go like this, they wanted it to go like this, but eventually it was going to follow logistic growth because that's what every virus always does. Exponential growth, swoop, where's ln? Well, if that's exponential, ln's doing the other way. It's the inverse, the reflection across the y equals x. Anyway, ln has a vertical asymptote. Basic graphs are important for lots of reasons. Anyway, ln, it's a swoop. Boop. Except, wait a minute, this ln's been shifted. How if it's an x plus 9? Where has that been shifted, guys? To the right or to the left if it's a plus in the inside? To the left. So it's been shifted over here to, well, 1, 2, 3, 4, 5, 6, whatever. At negative 9 is now my asymptote, and there's my ln. Everything's been shifted to the left now. Which means my domain is x greater than negative 9. The vertical asymptote is at the 0. This is all pre-cal. Negative 9 is the vertical asymptote. But guys, how's my interval looking? Is that okay? Yeah, x greater than negative 9. These numbers are. Cool. ln, anything sharp? Nope. It's all smooth. Cool. It's differentiable also. So I have differentiability. I also have continuity. So yes, MVT can be applied. So then if MVT can be applied, find C. Who is this guy and where did he come from? Ooh, and how could he have been rewritten in a very different way? All good questions for us to ponder real fast and solve. So let's just make this like yesterday's example problem. Let's make this like the problem that you guys had on the board that you found was the easiest one. Number 82. Just apply MVT. So, tell me the theorem one more time, one last time for today. MVT guarantees, as long as f is continuous on a closed, differentiable, continuous from point to point, differentiable everywhere in between. What can I say again? F prime of C. Ugh, let's not use that. Keep going, equals.
F of B.
Are you guys okay if I go ahead and use f of negative 7? F of B minus f of A, good, which is negative 8, all over B minus A. Which will give me a negative 7 plus 8 is a 1. Well, that's kind of nice. F of negative 7, I have to go plugging in. Negative 7 plus 9, isn't that 2? And then ln of negative 7 plus 9, isn't that ln of 2? F of B minus, plugging in negative 8. Negative 8 plus 9 is 1. ln of negative 8 plus 9 is ln of 1. Hey, is there anything special about ln's that we should know happens whenever I have a logarithm of a 1? Oh, struggle bus, guys. Remember, ln. swoops. And where does he swoop? He always
0.
1, 0. Yeah. 1 is always the 0 of logs because logs are exponents backwards. Says what exponent of a base e would make a 1? Every log is 0 at 1 because anything to the 0 power equals 1. So at the end of the day, all I'm trying to do is take my f prime of c, whoever he is that we'll find a derivative in just a second, and set it equal to, well, minus 0 goes away, over 1 stays the same, so 2 ln of 2, which some would call ln of 4, because of this little snazzy thing called the power property of logarithms. 2 squared is 4. But I'm not done. Why not? You guys saw it yesterday. Don't you have to set the derivative equal to that and then solve and find c? So how do I derive when I have something called a product? Oh, come on, come on. How do I do a product rule? I have to do a product rule. I have a times. The times is right in between. Boop. So product rule says what? Square times triangle prime, you can think of it that way. That's technically my second step. First d second, so I'm going to put that right here. But yes, square triangle prime is my second step. So first d second. Derivative of ln is 1 over u times u prime. And the derivative of x plus 9 is 1. And then if you're doing triangle square prime, which is technically what I do first, but some do it in a flip-flopped way. Second d first, I would have my ln of x plus 9. Derivative of x is 1, derivative of 9 is 0, 1 plus 0 is 1. Just how I'm doing that derivative. We end up for our f prime of x being ln of x plus 9. X plus 9 over x plus 9 reduces. That's just a big old fat 1. So then if I try to go solve, I'm coming up here and I'm saying, sweet, f prime of c is ln of c plus 9 is equal to ln of 4. If you remember the one-to-one property last year, one of your favorite things to learn, if I have logarithms matching, I can just say c plus 9 is equal to 4. Oh no, my bad. I totally forgot to write my plus 1. One-to-one property is not going to work. I didn't write plus 1. So then if there's not just an ln equals an ln, struggle bus, we have to do a little more work. Forgot my poor little plus 1. It's not just an ln, so I can't do that. I do want to use an e to get rid of an ln. I need to get the ln by itself first. This is going to get messy if I write it ln of 4 minus 1. You're like, what, ln of 3? And I'm like, no. It's ln of 4, all subtracting 1. So I'm going to write that as a negative 1 plus ln of 4. Now I can do an e because the ln's by itself. I have c plus 9 is equal to, whenever you have powers, exponent properties, they're powers being added or exponents being added. Exponent properties, it was multiplication of like bases. That's only if you want to make this look nice. We can go back and look at your, what's wrong with this part of my board? We can go back and look at your classmates' way of answering this because I think they just kind of kept it unsimplified, which was okay. WebAssign says yes. Subtract the 9. E to the negative 1 is going to be a 1 over e. E to the ln of 4, those just reduce, negative 4. So we end up with 4 over e minus 9, or you could get a common denominator, 4 minus 9e all over e. And that would have been the correct multiple choice match. I'm going to keep kind of that work up for anybody who's still using it for a couple more seconds. If you notice, you could keep it unsimplified, totally fine. You could keep it unsimplified, which would have been right here. E to the negative 1 plus ln of 4, subtract the 9, you got it. But you could also make it all nice and pretty and make it match exactly what they had. By an exponent property thing from Algebra 1, technically. Addition, but you're going backwards, which is weird, but we've used this before this year. Addition is multiplication of like bases. We do that so that we can legally get rid of the ln. which is much simpler. E to the negative 1 is a 1 over, and a 4 over a fraction and a non-fraction. We can get a common denominator and combine. Okay, that was the last question on 3.2. Let's get over to 3.3. That was that guy. You guys were supposed to watch a video. So you, with me, this year, live, have done none of this section. Well, very little of this section. Unless you've come in after school. So let's go check out 3.3. Why am I leaving WebAssign then? Because that was old school. That was a textbook, right? So old school in the textbook. Section 3.3. For those of you that were confused, let me quickly just make sure everybody else is good. These were the answers to the derivatives that you would have needed on any problems that had you go through the full process. Which is why I say, oh no, I did all this in class. Which is why the homework problems themselves you should have gotten from the WebAssign assignment, because not everyone needed the full process, so not everyone needed derivatives. So I actually gave you a hint and said, hey, these are the ones that need those derivatives. I'm going to go ahead and keep that up. I'm going to kind of regret my life choices for a couple seconds, because to get your online book, I need to open up WebAssign again. Go team. I know. But as I do that, those of you guys that need to transition with me, remember there are textbooks up here if you want to come grab them. I did not make copies of the book for this because you guys were doing this over break, or you were supposed to be. And you have an ebook on WebAssign. If you want to get into it like I'm getting into it, feel free. And or you can come borrow a book to have throughout class. Totally fine. Yeah, come on, grab it. It's the big blue one, right? So, Chapter 3, Section 3. Chapter 3, Section 3, the exercises. All right, let's go see which ones specifically you guys have questions on. Now, just to know, the people that ask questions, some of them have come into Math Lab and gotten other questions answered. Just because these are the only 3 that are currently on the board, that just means that those are the 3 questions that someone was brave enough to ask, they still have. That doesn't mean they were the only questions that they had. Does that make sense?
Misty, we're supposed to use the attachment. We're just supposed to look and see if the derivative is right.
Yeah. And if the derivative is wrong, make the change before you do the whole rest of the problem.
And critical number.
Yeah. And, well, you'll see me do it in number 11, right? Because that's the very first one, I think. So watch me in number 11 use the handout. Is that cool? Were there any questions before number 11? No. Okay, so number 11, this is the first, not the first one of homework, but the first one using the full process, and also the first one on, oh, hey, speaking of number 11, it's a pink one. Does that mean anything? Does pink mean anything? Doesn't it mean you can scan the QR code and go to CalcView and watch a teacher do the whole problem for you? Do some of us need that reminder? Probably. We like the pink ones. It's been a while since we were in the textbook. Hey, wait a minute. So the ones that are on WebAssign that match up perfectly with the textbook, are some of those pink problems that you can actually watch teachers do for you? It's been a while since some of you looked at that textbook, and maybe you forgot what a cool resource it is sometimes. Might not be a bad idea if we do go back to WebAssign, because you guys like getting to keep your answers unsimplified, knowing whether it's right or wrong, troubleshooting before you come to class. Maybe it's something good to think of. I should open the e-textbook and see if any of these are pink, because that'd even be better than a watch it, maybe. Anyway, coming back. Maybe they are the watch its. Honestly, I don't know. Okay, number 11. We are supposed to be, this isn't the full process, but it is the first half of 3.3, figuring out where this thing is increasing or decreasing. What? Awesome! Let me pretend to be some of the honors pre-cal kids yesterday that had a unit circle quiz and were devastated when I told them, after weeks of us learning the unit circle and practicing it, that they couldn't use their calculator on the quiz. Why would I let you use your calculator to answer 3 unit circle questions with what is sine, what is cosine, what is tangent if we've been learning it for 2? Exactly. Do you understand? So if any of you would be devastated if on the test I said you couldn't use your calculator, you're like, what? I was graphing them and looking at it. That's not how you do these problems. Hey, you are as powerful as you allow yourself to become, and you are as weak as you have, once again, caused yourself to become. At least mathematically speaking in your skills. Coming back. There was a little bit of confession by glance just a second ago. So when this test does not have a calculator, we're not going to complain. Because why would I teach it the calculus way if it was just to be using Desmos or GeoGebra or your grapher? Okay, looking at this function. How do I know where he's going up and going down? I don't yet, but I'm about to. And how do I about to do this my way? You can watch and see how the other teacher does it. How do I do it my way? My way that you should have already watched on the video. My way, actually, let me do this so that way. Ooh, look, it's the answer. We can see if we got it right or not. My way that you should have in your notes. My way that is also in the current Jamboard that some of you, if you have not watched the video yet, could be currently taking the notes. Because I have gotten all of the notes that were in the video up on the Jamboard. Actually, no, hold on. I apologize. This guy, you guys, I don't think you have access to edit this one. There you go. Perfect. A couple examples I didn't get to way back then. Here's my process. How do I figure out where it's going up, where it's going down? I start by saying, what's the domain? Are there any discontinuities? Because they would need to go in the sign chart. What are the crits? We've already talked about those, so I can put them in the sign chart. Who is a sign chart? And what does the sign of the derivative tell me? And I'm going to test each and every interval formed by the discontinuities and the crits. Because all I need is one sign. Basically, IVT tells me whatever it is, it'll be for the whole time until this, and it might change or it might not, might change or might not. And then I'll go from there. So I'm going to go ahead and bloop. I did not take a new picture. I'm going to take a new picture. There he is. Boop. And let's go. How do I get these answers without a calculator? P.S. How would you get it with a calculator? Wouldn't you have nasty decimals? And nasty decimals you try to put into a WebAssign and then it wouldn't work? Lucas, go for it. Sure. P.S. He already has this one done, I know. Square root. Square root has a limited domain. Square root says whatever is underneath me has to stay positive. That has to stay positive because otherwise negatives would make imaginary numbers. This does have some discontinuities for me to think about, or at least some limited domains for me to think about. Specifically, x is going to have to be between -4 to 4. I'm going to leave you guys to think about that. If you want to come talk to me about how to actually be able to have the power to do that yourself without a calculator. And without looking at it, 16 minus 16 is 0. That's one boundary. 16 minus 16, if I plug in a -4, that's another boundary. So 4 and -4 my boundaries. Ultimately, we just test. If you plug in a 0, it works. So in between is good. If you plug in a 5 or a -5, it doesn't work. So therefore, those are bad. That's the math of how to check. I have a limited domain. That means my sign chart is only going to go from 4 to -4. That's it. I don't have all real numbers. My sign chart, my increasing, decreasing sign chart, this is what 3.3 teaches you. If you don't believe me, this is important, come in and let me open up any and every practice test that's in that Barron's book or that's been given online, and let me count up with you staring exactly how many use this idea or the one that's following it in 3.4 that's built upon it. Guys, there are many, many, many on every AP test that have ever been given. Any AP test that has ever been given. You slack right here, you're basically paralyzing yourself from the AP. Maybe not from the rest of the year, but you are from the AP. Which is 2/3 non-calculator approximately. Okay, as we come back here. What am I doing? I'm admitting the depravity of man, and that some of you are making unwise decisions. I'm trying to challenge you to stop and choose better. Choose life. Choose AP life. Hey, that's biblical, not the AP part, but the other part, so maybe we can apply it to calculus. So, as we come here, I know my domain. I know my domain is limited. I need to go looking now for crits. For crits, I'm going to be looking at the derivative. For the derivative, I have to take it. Hovan just asked me, what do I use that sheet for? Well, let me show you. You were supposed to be finding y prime. As you find y prime, it's going to be a little messy as you do that second D first. As you remember, you just go the other order, that's okay. Second be first, plus first be second. Yours would just be switched, right? First be second. Oh no, we have to think about how this is to the 1/2 power, right? 1/2 power. A lot of us, if you've been putting into proper practice, you know what's going to happen. The 1/2 comes down, that becomes a negative 1/2 when you subtract 1, which makes a square root in the denominator. Which is why I'm going straight to 1/2 times the square root of 16 minus x squared, except, hopefully you also would not forget your poor little bunnies and your chain rules. You have a u prime of negative 2x as well. Now, even if you're like, psh, that wasn't bad, I know how to do my product rule even if I have square roots. Even if you knew how to simplify this and make this look better, it's still messy for what you need to do because you have a fraction and a non-fraction. P.S. This was asked of me several times after school, which is once again why some of your classmates don't need to be paying attention because they can be taking 3.4 notes or maybe finishing up 3.3 notes or maybe getting things turned in and pictures taken on Google Classroom. It's a hard one. Why is it hard? Because I want crits. But to find crits, I want to pitchfork it. But to pitchfork it, I want a nice numerator to set equal to 0 and a nice denominator to set equal to 0. But I do not have a nice numerator because a numerator indicates 1, and right now I have 2 different numerators to 2 different denominators. I'm going to save the critical number process for a second, and I'm going to say, hey, old school, my life is easier if I get common denominators. Which is why I gave you that nasty worksheet that says derivative simplified. This is a correct derivative. That is a correct derivative, but for your crits, you needed the derivative to be simplified. A square root squared makes it go away. That actually makes things much nicer. And then I still have that little minus x squared, and I have common denominators now, which is why I'm bringing them all together. With one quick simplification, I now have something to find crits from. The zeros at the top, which are my horizontal tangents, will end up being x is equal to plus or minus square root of 8, which is the same thing as if you simplify that radical 2 rad 2. And on the bottom, I get x is equal to plus or minus 4, but we already know that because that is how my function is limited if you did the domain step. So actually these will not be crits for me to put between because I already have them because of my domain. Now I'm going to go ahead and throw in whatever fits, which actually both of them do, the negative one and the positive one. You have more power than you think. 4 is 2 times 2. 2 times root 2 is smaller because 2 times 2 is 2 times root 4. Well, 2 root 2 is smaller than 2 root 4. You have more power than you think. I don't need to know the decimal to know that that falls in between. This whole section says, how do I know increasing and decreasing? I know because these are the only possible transition points. Critical numbers are the only possible transition points of a function's behavior. It will either change at a sharp point, or it will change at a smooth horizontal tangent, or it will change at a discontinuity. That's the only possible way any function will change behavior. So then I just need to say, what's going on here? Testing 1 point. What's going on here? Testing 1 point. Testing what? Well, I'm testing the derivative. Where's the tangent line? Because that shows where it's pushing. Is the tangent line up? It's pushing up. It's increasing. Is the tangent line down? It's pushing down. It's decreasing. It, meaning my function. So then I just need to go ahead and say, we got to plug a few things into our derivatives to know our behavior. So f prime of, I have 4 different tests to do. I'm showing it just so you have a visual. I usually do this in my head. What's something between negative 2 rad 2 and 4? Well, the bummer is it's not negative 3. Oh wait, I only have 3 intervals. Sorry, there's only 3 betweens to check, right? There's that one, and that one. I'm going to be lazy for a second. I'm going to say, well, at least I know zeros in between these two. Let's check 0. Plugging into the derivative and saying, what is the slope of the tangent line? Plugging in 0. That's a positive. Okay, cool. So I know this for my derivative, which means my original function is increasing. I know my original function is increasing between negative 2 rad 2 and 2 rad 2, which is exactly what that answer says. Or what I am supposed to put down as my answer for the interval on which my function is increasing. For decreasing, we would have to get a little bit more exciting. I meant to make that red, sorry. You can already tell up here that they are going to end up both being negative when I do plug in, which is going to have or show me that those functions are, or that function is decreasing on both of those intervals, this one and that one. Last year in pre-cal, we learned that we would use the union symbol. That's the proper way to connect or to link those two. How would you know that? Well, I mean, it's kind of lame. It's kind of lame, but one way is you could just be like, well, what's negative 3.9 and positive 3.9? I know that rad 2 is still pretty far away from rad 4. You have rad 3 in between, so you could do something like that. Technically,
Why can't you do 3?
because this is bigger than 1. Oh, bigger than 1, that doesn't mean it's bigger than 3. And 4th is bigger than 2. Oh, sweet. Negative 3 does work. You guys are wondering why? You heard Havan ask, why can't you use negative 3? If you're wondering what I was doing, I was saying 2 rad what would be 3. Seeing if I could use it. 9/4. 2 rad 9/4 makes 3, which is bigger than 2, because that's 2 1/4. So yeah, never mind, I couldn't use 3. It's a lot easier. And the reason Havan is like, I really don't want to do 3.9 and negative 3.9 is because I would have to square it, multiply it by 2, and compare it to 16. So since I can use negative 3 and 3, life is a lot easier. Because 3 squared is 9, 2 and 9 is 18, 16 minus 18 is a negative number. And when I come down here and do 16 minus 9, that's a positive number. A negative over a positive is a negative. And that will be true on both sides. And you have your final answers. This is the first live in class example of the first half of section 3.3, once again, whose process is here, of how to analyze a function for increasing or decreasing. On the video, did I do examples? The answer is yes, which you should have already watched and should have already taken notes on. I'm reminding, make wise choices based thereupon. The other question, 2 questions you guys asked. 42, I'm hoping, is this a relative min-max? Nice. If you guys are wondering, the next section starts off doing the exact same thing. The next section, A and B, is doing exactly what we just did for any of these functions. Hey, look, one of them is pink, whether or not I assigned it. You could watch it. A and B is exactly the process I just did. C says, let's take it one step further, and this is the second half of 3.3. C says, let's take it one step further. And that's the second half of section 3.3. So when we do number 42, which is a piecewise function, we're doing everything that we just did, and we're going one step further, which would have been nicest for me to show you for a non-piecewise function, but oh wait, I wonder if maybe that was something that was done on the video. Okay, so here we go. For a piecewise function, number 42, excellent question. How do we do everything that we just did on a piecewise function? First of all, I would think of domain, always the first step. This says all x's less than negative 1 work, all x's greater than negative 1 work. There's no denominators, no ln's, no tangents, nothing to restrict or cause discontinuities, no denominators. The domain's all real numbers. So I have no discontinuities to worry about. My sign chart is just going to be all numbers left, all numbers right. I'm not marking anything because the only marks that go when there are discontinuities of which I have none and critical numbers which I don't have yet. Critical numbers come from what, guys? And why am I getting red? Where do crits come from? This is not 3.3, this is 3.1. Where do crits come from?
Setting the derivative.
Setting the derivative equal to a pitchfork. So derivative. This is where it gets a little interesting. I have pieces. So how do I derive if I have pieces? Piece by piece. Yeah, Josh. Yep. Piece by piece. Oh wait, hold on. Why am I going to stop writing the second piece and I'm going to erase the negative and say I'm good? What's the derivative of 2? 0. Derivative of 2x is 2, derivative of x squared is 2x, and then the derivative of 1 is 0, derivative of 2 is 0. Now, critical numbers. We're trying to find where the derivative is 0 or the derivative does not exist. I'm not writing that top inequality for a very important reason, but let's pause and think. First of all, guys, which of these could be 0? And if they could, when would it happen? Can 2 ever be 0? The number 2? No, 2 doesn't equal 0. Can 2x be 0? Totally, when x is equal to? So, but wait, hold on. This is only true for some x's. Is 0 greater than -1? So, that works. Check. Okay, yeah. If x is 0, which is greater than -1, I'll be looking here. 2 times 0 is 0. The derivative will be 0 at 0. Where's the only place the derivative for a piecewise could not exist if the derivative is 2 for the whole left side and the derivative is 2x for the whole right side, which is an always existing number and an always existing expression? Where's the only place it could not exist? The derivative is a limit. The only times that limits can't exist are if the graph is if the original graph is sharp, which means that the slopes would not match. Whenever the approaches do not agree. Remember that? Whenever the approaches do not agree. When I have something that's broken. And kiddos, where is the point in between the left and the right side?
0.
No, not 0. What's the x that's in between the left side and the right side? -1 is the separator. On one side of -1, everything's fine. On the other side of -1, everything's fine. The problem is at -1, do they agree? So the derivative exists, or do they disagree? So the derivative does not. So we would need to take a quick little limit and say, hey, Mr. Derivative, how are you doing? Come into a -1 from, I guess I'd come from below first, probably. Here's a big question mark, to know if there's a DNE or not. So I would say, okay, coming from, I have to look here. I guess I could say less than. The problem is I can't put an or equal to unless they match. Derivatives are limits. Limits, there has to be an agreement. At -1, there could be a disagreement. So below -1, I'm plugging into, oh, I'm looking at that derivative. And above -1, I'm looking at this guy. Oh! Do these agree or disagree? 2 at -1 is just 2. 2x at -1 is -2. Agree or disagree? Disagree. If they disagree, then I have to also include -1. I have 2 crits. I had a disagreement going on at -1, that's a DNE, and then I had a 0 going on at 0 for my derivative. That's a horizontal tangent line. Those are my 2 crits. Once I have my 2 crits, I go through my process. Remember, so far we're just doing what we did in the last example. I'm going to test. Except this time I'm not going to like literally write out, plugging in every single interval and checking if it's positive or negative. I'm just going to kind of do it right up here. I'm going to pick -10 and say, okay, cool, -10. Let's come up and look. Negative 10 is less than, which is 2. Two is a positive number. Then I'm going to plug in negative 1/2. Negative 1/2 is greater than. Plugging in negative 1/2 would be a negative. And then I'm going to plug in something like 10. 10 is greater than. That would be a 20, which is a positive. So I have my function increasing, then decreasing for a very little bit, and then increasing for forever. What does that mean? I could go ahead and for letter B, I could talk about my increasing intervals, I could talk about my decreasing intervals, but what I'm focusing on instead as far as this problem is, you can see it in the sign chart. You would use the x's to make those answers. Things like from negative infinity to negative 1, it's increasing, and then again from 0 to infinity. From negative 1 to 0 is when it's decreasing. But they were asking one more question, and that one more question is, are there any relative extrema? So when you watch the video, after you take notes, the first derivative test says if you have analyzed a function for its behavior based on the first derivative, you can find any relative extrema if they exist, because a relative min will always be the point between which a function changes from decreasing to increasing, or the point at which a function changes from decreasing to increasing. A relative maximum will always be the point at which a function changes from increasing to decreasing. P.S. This is not a vertical asymptote. This is not a hole. This is not a discontinuity. It's only at a crit where the change occurs. Sharp or horizontal tangent lines. And then if the sign doesn't change, it's definitely neither of those. So then if we just think about the behavior, is there a relative max? Of course there is. It's right here. And that's going to be at the point negative 1. We'll find the y value in a second if they want that. The minimum is going to occur right here based on the behavior. If it wants the y value, give me a second, and then we'll get that. But those are the x's at which they occur. The y values, we have to come back here to the original function. These are the y's. Remember, this guy, he is the slopes. I don't want slopes if I want to know how high or how low, where the point is at. I want the y. So I would come over here and say 0 is greater than, plug it in, 0 minus 2 is negative 2. Negative 1 is less than or equal to, negative 2 times negative 1 is negative 2 plus 1 is negative 1. And all I'd have to do is put it in my graphing calculator and see if I actually found the proper min, the proper max without using technology and just using my brain. What is that sheet that I have in the attached homework? Number 11 had the function, had the derivative, and had the derivative. They went ahead and factored it. I just would have solved that top equal to 0 and gotten a plus 8 and then a plus or minus square root. They just showed how you get both of them. But they have the function and the final derivative and how to get the crits from it. That's what each one of those has, because every time you have one of these problems, it can be very tricky. I only went to the answer key and I snapshotted that one little piece of the work for every single one. Andy, I did not do it myself. I went to CalcChat, my version of it that has everything, and I grabbed every single piece of where they did the derivatives and how they found the critical numbers so that you guys wouldn't be having the wrong one and do this whole process at the wrong numbers, because then that is a huge, huge, huge discouragement. I wanted you to be able to make sure your derivatives were right. Last but not least, number 103. Last but not least, number 103. For what?
For one more.
Let me get 103 first, and then maybe. Although we had a whole section to do, and a lot of what I'm answering is not people that got momentarily stuck, but a lot of what I'm doing is for people that didn't do the work that they were supposed to by watching the videos and taking the notes, so we'll see. In 103, 104, the graph shows the position of a particle moving along the line. Describe how the particle's position. Oh, it's pre-calc, kids. No. I know it sounds rough. I don't mean for it to sound rough. I mean for it to sound encouraging. This is just position. You're able to see what it's doing. What is this doing? Well, it's either moving right or left or up or down. It doesn't really say. Oh, along a line. Let's just assume it's moving along a line. And as this little particle is bouncing and going back and forth along a line, it's bouncing off or around or on a line. As it's moving, how do I know it's moving back and forth? Well, because sometimes it's going up to 24. So wherever 24 is, that's the highest up it goes, or the highest right it goes. So it goes to 24. Then what does it do? Well, then it comes down to like a negative 1-ish. So if this is like the 0, because it starts at 0, it goes up to 24, then it goes back to like a negative 1, then it comes up to an 8, so then it comes back here, then it bounces down and goes a little more negative, then it comes back up. So anyway, this thing is bouncing back and forth across the line. If I just showed you and said, hey look, that's what it did, and I just showed you that, you're like, I don't know what it did. But if I show you this, how it's being mapped out over time, you're like, oh, it's going to the right, and then it's going to the left, and then it's going to the right, then to the left. But they're not even asking that much detail, because they didn't tell you right or left or up or down. I'm not sure what kind of line, or even I'm not sure what line it's on, but I can say it's increasing and decreasing for certain intervals. And this isn't me thinking about a derivative. I mean, you can think tangent lines. Sure, tangent lines are positive. It's increasing. When? Well, up until 1. So it's increasing from 0 to 1. Then it decreases from 1 all the way to, it looks like 3.5. Then it increases again from 3.5 to 5 maybe. And then it decreases from 5 to what looks like 7, no, 8, no, 7.5-ish. No, sorry, 5. And then it increases again from 7.5 until like 9.5. If you guys look, I'm going to erase what I just did. It technically has a little baby decrease right here at the very end. There's a little relative maximum that would be hard for the eye to see, but the calculus would have a critical number. The sign chart would show it's obviously there from 9.5 to 10. You're not in web science, so it's not going to be as big a deal, but you should be using those union symbols to connect each of those intervals. And I believe that's all it's asking for in 103. Hovan, that went pretty fast. Let me freeze the screen for people looking at it. And what was that last question that you wanted to look at?
It was 53. It just doesn't have critical numbers.
Oh, 53 on the homework number, the handout? Oh, why it doesn't. Okay, let me just zoom in and talk about that. Yeah, I hear you. That was definitely one that was worked through in math lab. Number 53, even after you do a quotient rule, even after you get common denominator, well actually quotient rule, if you did it that way, you would have a nice fraction. So even after you did the quotient rule and you simplified after the quotient rule, what do you do if you're supposed to be doing this whole process and there are no crits? First of all, you double check there was no domain issues. Domain issues, e to the 2x plus 1, there's a division, that can't be a 0. But if you go and you get e by itself, if you know how to undo an e with an ln, ln has to be greater than 0. That's impossible, because ln of a negative will never happen. You can't raise something to a power and have it be a negative if it was positive to begin with. So since that can't happen, my domain is just all real numbers, so there's nothing there. And there are no critical numbers, so therefore when you do your sign chart, you still do it. It's just your job has gotten not infinitely, but has gotten easier. Because remember, you only have to test 1 point.
Not 0.
Not 2, because it hasn't been split up. Not 3, because it hasn't been split up. So sure, plug in 0 if you want. If you plug in 0 to your f prime, it will tell me what this is doing the whole time. Maybe not how fast or how slow it's doing, but it will tell me it's always increasing or always decreasing. And when I plug in 0, I get 2e to the 0. Anything squared is always a positive. E to the 0 is 1. Anything to the 0 is 1 times 2 is also a positive. A positive over a positive is a... This guy is increasing for forever, which makes him one of the easiest ones to answer. Because I can just say, oh, sweet. I mean, his derivative was rough, but he never changes behavior, so therefore he's increasing forever, and he has no relative extrema. Why? Because he doesn't change. So there is no min, there is no max, because he's always going up. Other stuff could be changing, but not in a way that would give him a peak or give him a valley, because he only has one type of behavior, because there was no domain issues or critical numbers to have it possibly switch. So yeah, good question. 53 is going to be up here for about 5 more seconds, but I did just say a second ago, I'm leading into 3.4, everybody. I did just say something could be changing. Something else could be changing, but not his increasing, decreasing behavior. It's dumb for me to waste everybody's time by harping on this too much, so I'm just going to merely say if all of that was foreign to you, it's because you have not properly done your homework, and you probably haven't watched the video for 3.3, even if you have the notes, which some of you don't. Someone who did take notes properly on 3.3, can you quickly just give a shout out of how many pages you used? Because some of your classmates now need to know that fact to skip those numbers of pages to go to 3.4. How many pages did 3.3 take? About 3 pages. 3 sides or 3 full pages? 3 sides. So skip 3 sides. If you didn't take those notes yet, please get it done ASAP. And here we go in 3.4, because going up and going down is not the only thing to talk about. Going up and going down is not the only thing to talk about. What else there is to talk about is how it's going up or how it's going down. It could be going up in a slopes increasing kind of way, or it could be going up in a slopes decreasing kind of way. I'm getting out of 3.3. All of those notes are updated. I think they're updated on the Jamboards as well, because I tried to get those in for you guys. Let me freeze the screen so that you guys can get the first page of 3.4. There is another key characteristic we have to talk about, which seems random, perhaps, except it's very important for the shape of a curve as to whether it's not just going up, going down, but also whether it's going up in a concave up way or going up in a concave down way. Going up in a concave up way says it's going up faster. Going up in a concave down way says it's going up, but it's slowing down. And knowing whether it's going slower or faster could be a very, very, very important piece of information when trying to analyze behavior. Go. P.S. He is not at all in charge of that study in any way, shape, or form. He literally just saw a company and he knew that they were doing a launch. And he's like, I wonder what they're doing. And he Googled it and he was like, oh, cool. He's not like the one inside the hangars or anything like that. If I'm talking about concavity, if I'm just thinking about, oh, you want me to make a graph not using a calculator? This is stupid. I have a calculator. But if you think instead, no, this allows me to describe the behavior, analyze the behavior, predict what change could be happening down the line. That's just not like, hey, let's look at a calculator sort of thing. And remember, everything that you guys are seeing are very, 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 very basic functions, even the hard ones. There is math out there to deal with the fuzziness of life, where there's not a nice function just to describe it. But those are levels far beyond where we are now. But concavity is also important for us to think about. Whether a behavior is decreasing, but in a concave up sort of way, or whether it's decreasing in a concave down sort of way, whether it's increasing in a concave up sort of way, or if it's increasing in a concave down sort of way. These are all very important things to know because as you guys can tell, once again, can I just quickly show you something that will be a precursor to what's to come? This would be something that's speeding up. It's really obvious to see because those slopes are getting steeper, but it's speeding up in a positive direction. Does anybody know the one other one that shows speeding up? What other one shows? Only one other one. The other two are slowing down. What else is showing speeding up?
Top right.
Actually, no, but a lot of people would say this one because it is increasing, but what's happening to the slopes, which indicate the rates? They're flattening or going to zero. It's not this one because the slopes are flattening. Not this one because the slopes are flattening. Technically, this one we would say the velocities are increasing, and this is where things get really confusing. The velocities are increasing. Negative numbers are getting more and more and more towards the positives. Negative numbers are coming into zero, which is increasing on a number line, but do you see the flattening nature? He's slowing down and he's slowing down. If they flatten, they're slowing down. This guy is the other speeding up one, but he's speeding up in a different direction. He's speeding up in a different direction. And so, that's why it's important to not just say something's going up, but to also say something like, oh, it's helpful to know if the slopes are getting steeper. And in this case, it's increasing and in a steeper way. But here's the struggle. These slopes, actually no, these ones are decreasing. Positive numbers getting less positive. Slopes decreasing in a flattening way. But let me come up here without drawing all the slopes. This was for this branch right here and this branch right there. Let me talk about these two real fast because I didn't mention them down below. This one, the slopes are actually decreasing, which a lot of people, if you just saw the words, would say like, oh, velocity is decreasing? It's slowing down. But it's decreasing in a steepening way, which means actually speeding up. And then this one, the slopes are increasing. Negative numbers like I already talked about. Coming up on the number line, the slopes are increasing, but in a flattening way. There's much to learn. There's much to learn. But let's just talk about something real fast about how does this or where does this correspond to concavity. Slopes increasing here and slopes increasing here. Check it. What's the same on this graph and this graph? Is they're both concave up. Slopes increase on concave up portions of the graph. Now careful, some get steeper, some get flatter. So we can't just say this is speed necessarily. Speed has to do with magnitude, absolute value. It's a little tricky. And what's true if the slopes are decreasing, even though the flattening, steeper thing might change, what's true is that you have this concave down nature. Okay, that's all well and good. I'm just saying that maybe concavity is something we should talk about. But how do we talk about concavity? Right now, are you guys still at this page in your notes? Can you really quickly make a big fat F double prime for section 3.4? And can you go back to 3.3 and make it a big fat F prime? The big difference is whether you're looking and dealing with the first derivative or whether you're looking and dealing with the second derivative. And in many ways, that's the only difference. In many, not all, but in many ways, that's the only difference. So any of you that paid attention today and saw me look at domain, and saw me go and take a derivative, and saw me make it simpler, and saw me do a pitchfork, and saw me take those special numbers and put them in a number line, and saw me test different signs, we're doing the exact same thing. But now with the second derivative. And then we're going to kind of have to, which is probably what we'll mostly do tomorrow, discuss, solidify, okay, what does this actually tell us But the process, oh my goodness. Look at what I did. I squished it into one slide. Why? Because it's so similar. If I can know the second derivative is positive or negative, then I know its prior derivative is increasing or decreasing. Increasing or decreasing is told about whatever is one step back in the differentiation process. If you have a first derivative positive or negative, then the original is increasing or decreasing. If you have a second derivative positive or negative, then the first derivative is increasing or decreasing. And that increasing or decreasing of the slopes is what shows me concavity. This card, so similar to the increasing decreasing test card, but it's talking about the second derivative. And what's all this? This is so similar to that blue screen in the 3.3. It's just saying, what do I do for the second derivative? Now guys, if I were you, I'd take a picture of it. I'd get on the Jamboard, I'd copy it down. Have this ready for me tomorrow. But pause and think. Pause and think. If I'm using the second derivative, think about the math. Those of you that worked on 3.3, think about the math. Think about when it got hard and not conceptually just like blood, sweat, and tears in doing the work. If I need to use the second derivative, what am I going to have to do? Start at the original and do what? Derive it once. Derive it again. And get that one simplified. Could that be messy? Yes. Which is why, once again, we're in our textbook. Which is why, once again, I have attached, those of you that didn't know it and understand it the first time, which is why, once again, I have attached a cheat sheet. What's that cheat sheet? Do you know how to find both derivatives and get them simplified? And once again, actually, do I? Yeah. Although this time, do you guys see them calling them critical numbers? You see them setting equal to 0, but do they say crits? They're setting them equal to 0. Are they calling them crits? No. Why? Crits are defined in 3.1 to be talking about the first derivative. Section 3.4, second derivative, they're going to have different names, but if you notice, our book doesn't use a different name. It just says find the zeros. Zeros and DNEs technically, but so far, oh, they're only zeros, only zeros, only zeros so far. All right, cool kids. I'm going to put this back on the screen if somebody did not take a picture. This needs to be in your notes. Have your notes totally caught up. Ready to go. By tomorrow, 3.3 and 3.4. And if you guys have that tomorrow, I'm making a deal with you. Careful, deal with the devil. Oh, one person can ruin it for everybody. So if I were you, I would AirPods out. One person can ruin it for everybody. The deadline for 3.4 homework is tomorrow night, 11:59. If everybody has their notes, AirPods out, everybody listening. If everybody has your notes caught up to here by tomorrow, I will change that deadline to Monday at 3:30. But only then. You hear me? Ready, set, get out of here. Bye. I'm asking something very small. Have your notes ready to go for tomorrow with these written down. One person could ruin it for everybody. If you need a friend to text you, if you need a reminder on your phone, have your notes ready to go tomorrow.
That guy.
Just gonna be like that.
Is today Brache bread? Donut holes and Brache bread? Bye guys, don't forget December 10th.